This video is about expectation. What is expectation? It summarizes average values of random variables. So expectation essentially can be regarded as a function, maps a subset of the collection of all random variables to their expected values, which are numbers. Unfortunately, not all random variables have expected values. So this is a function work with a subset of the collection of all random variables. And it gives numbers to those well-defined random variables. Why do we need expectation? Well, we know distribution assign numbers to random events associated with the random variables, but those gonna be many values associated with many different events. Sometimes one would prefer to know what happens on average. One would prefer to have one value, a single value, to describe the general idea. For example, if we throw a fair coin for many times and get one which has 0 bottoms, we know from our daily experience the average will be roughly half. And that's the expected value we are talking about. Expectation formalizes this idea and assigns a number if the number exists for one random variable. Here is one example. Suppose we have x follows Bernoulli distribution with the following PMF. So x equal to 0 with the probability value equal to 1 minus p, and it equals 1 with the probability value p. What is the expected value of x? The expectation x is essentially 0 times the probability x equal to 0 plus 1 times the probability of the event x equal to 1, which is equal to p. And this is the average value or the expected value of x. Take this for another example, right? Consider a function of this random variable x, a linear function of this x, 2 plus 2x. It is also a random variable. And based on the construction, it's easy to say that the probability of this new random variable y equal to 2 equals the probability value of the event x equal to 0, which is 1 minus p. And the probability y equals 4 is essentially equal to p, the probability value of the event x equal to 1. And the expected value of y, we can follow the similar logic to derive here, which is 2 plus 2p. Given the y is a linear transformation of x, right? If we talk about the average, then from our daily experience, the average should also follow the linear transformation of the original average, right? So that is indeed what we have there. The expectation of x is equal to p, and the expected value of y is 2 plus 2p, which follows exactly the same linear transformation as the original transformation here. So for discrete random variable x, this is what we work with for the expectation, right? How do we determine the expected value for a discrete random variable x? It essentially equals a weighted average of possible values taken by x, and those weights are the associated probability values. So it's essentially is possible values taken by x times the probability of the random variable of the event that the random variable x equals that value. Of course, if we look closely, the expectation may not be well defined for some random variables. For the expectation, in this case, to be well defined, we need the condition that this summation is well defined. At least it should equal to some finite numbers. And for some random variables, this summation is not well defined. So expectation essentially maps a subset of the collection of all random variables to numbers. It's still a function. And given it discusses average values, it satisfies very nice properties for real values random variables. Right? If we consider the average value of this new random variable x plus y is equal to the average value of x plus the average value of y informally. If we consider this transformation, ax, transform the original random variable x by multiplying with a scalar a, then the average value of this new variable is essentially a times the original average value. So expectation has very nice properties. But at the same time, this is a very important concept because it goes far beyond average. For example, it can recover probability values. Let's consider this indicator random variable I given the event x equal to x. So this random variable equals 1 if x equal to small x and 0 otherwise. So this is essentially also a random variable, right? This is also a function of this random variable x such that it maps all the outcomes from the sample space that equals 1 if this small s belongs to the event x equal to x and 0 otherwise. It's also a Bernoulli distribution, right? If we look at the expectation of this indicator random variable, it's essentially equal to the probability of x equal to x, because it's 0 times the probability of this event not happen plus 1 times the probability of the event x equal to small x. So expectation goes far beyond the average, and this video only touches a surface of the idea. Thank you for watching this video.